Physics. The recent image captured by this telescope has generated compelling arguments that have surprised experts, putting an end to much speculation. The telescope's most recent discovery is visually stunning and could transform our understanding of the universe. The discussion among experts that this image has resolved centers on the perception of the cosmos. The stunning image taken by the James Space Telescope challenges our understanding of the universe. This finding addresses one of the main problems in astrophysics: the age of the universe and its rate of expansion. Scientists of different generations have been puzzled by this unsolved phenomenon and have carried out numerous studies in search of answers. Cosmologists investigate how the world originated, how it works, how it has changed over time, and how it will end. In the last 100 years, great advances have been made in this field. The Big Bang theory, the most widely accepted theory in cosmology, holds that the universe has been expanding for approximately 13.8 billion years, starting from an extremely hot and dense state. The Hubble constant, which indicates the expansion rate of the universe, is used to measure its growth. However, determining how to measure the Hubble constant is not straightforward, and there are two main methods: local measurements and measurements of the early universe. In space, objects such as stars and Type I supernovae, which are used as standard candles because of their constant brightness, allow astronomers to measure how far away they are and thus calculate the Hubble constant. As the expansion of the universe varies in speed, scientists can calculate the Hubble constant. There are two main approaches. One is the measurement of the early universe. Scientists use readings of the cosmic microwave background radiation, or CMB, discovered in the 1960s as the afterglow of the Big Bang. This microwave energy comes from when the universe was only 380,000 years old. Astronomers can determine the age of the universe and its expansion rate by measuring the tiny ripples of temperature and polarization emitted by the CMB. However, there is a problem. These methods do not yield the same result. Local measurements suggest that the universe is expanding faster than the CMB data indicate. Scientists have been hard at work trying to understand why the results differ. To unravel more mysteries of the universe, more studies are underway. The differences in measurement indicate that we do not yet know all the signs or that there are errors in one or both methodologies. But thanks to the James Webb Space Telescope, we can peer farther into the darkness of space than ever before, revealing elements, planets, and galaxies we never thought possible. Scientists hope the data found will help them calculate the Hubble constant, but the first wave of data has revealed new things that don't line up with our expectations. Could this information give us a new perspective on space? We may need to rethink what we know about how the universe works. We might discover particles and forces never seen before, or find that dark energy, an unknown force that accelerates the expansion of the universe, needs to be reconsidered. With each new discovery, our ideas about space have evolved. For example, the cosmic microwave background radiation discovered in 1965 was strong proof of the Big Bang theory. Before that, scientists thought the universe would last forever, growing at the same rate indefinitely. However, new evidence showed this was not the case. In the late 1990s, when we discovered that the universe was constantly expanding, we also learned about dark energy and its impact on this expansion. Every time we discover something new, we check whether it fits with our previous knowledge and generate new ways of understanding the universe. If it were not for this problem we face, cosmology could not progress. Instead, this problem drives us to find better ways to understand the universe. Although this problem is complex, it is also exciting because it drives us to develop better tools to explore space. Scientists around the world are interested in this cosmological problem because everyone wants to know more about the universe. Most importantly, this demonstrates how science is always evolving. As we learn more about space, another concept comes into view: sigma-8 tension. This concept goes hand in hand with Hubble tension and refers to how matter is distributed in space. We use this information to create a structure of the universe and see how it has changed over time. Some areas of space have many galaxies clustered together, while others do not. Scientists use different methods to determine the magnitude of this dispersion. One possible way to address this is to look at how different densities of matter, such as galaxy clusters, bend light from distant galaxies. This phenomenon, known as gravitational lensing, allows us to see whether the dark matter, which does not emit light and is therefore undetectable, is influencing what we observe. Scientists also analyze the cosmic microwave background, the CMB radiation, an afterglow from the Big Bang. This light has traveled for about 13.8 billion years, carrying information since the beginning of the universe. By studying the CMB, scientists can understand how the universe was full of irregularities when it formed. However, there is a problem. This data does not match the large-scale irregularities observed in the current universe. The non-spherical distribution of gravity suggests that matter in the early universe was more uniform than what we now see with gravitational lensing. This suggests that there is something we are not considering in our interpretation, which brings us back to the idea of dark matter and how it works. According to Adam Rees and his team, they were able to redefine their work thanks to the Webb Space Telescope and wanted to find out if a possible error in the Hubble Space Telescope measurements could be the cause of this discrepancy. However, the JWST showed the same deviations, which is worrying. Somewhere between these two observations, there must be a fundamental flaw in our understanding of the universe. Rees said in an interview with an astronomical magazine in the United States that using the new space telescope has allowed us to look deeper into the universe through its sharp infrared view and study cosmic distances with ever more precision. Both dark matter and dark energy are enigmatic components that make up a significant part of the universe, but their nature remains elusive. While black holes have been the leading explanation for certain gravitational effects, there is growing interest in exploring how dark matter and dark energy play into this picture. Dark matter, though invisible, is believed to exert gravitational forces that keep galaxies from flying apart. It is thought to form the scaffold on which visible matter clumps together to form stars and galaxies. However, despite its enormous inferred mass, we have yet to detect a dark matter particle directly. It interacts very weakly, if at all, with electromagnetic forces, meaning it doesn't absorb, reflect, or emit light. Meanwhile, dark energy is even more mysterious. First inferred from supernova data in the late 1990s, it appears to act as a repulsive force, pushing galaxies apart and accelerating the universe's expansion. The JWST's unprecedented infrared clarity is offering scientists a new way to observe the structures of distant galaxies and how they evolve. Its sensitivity allows astronomers to observe the light from the earliest stars and galaxies, forming when the universe was just a few 100 million years old. These observations are critical to testing our models of dark energy and dark matter and refining our understanding of the universe's expansion history. Some theories propose that dark energy may not be a constant force, as Einstein originally proposed with his cosmological constant, but could instead vary over time and space, a concept known as quintessence. Other radical ideas involve modifications to gravity itself. Perhaps general relativity breaks down over vast cosmic distances, requiring new equations to accurately describe gravity on a universal scale. These alternative gravity models attempt to explain the accelerating expansion without invoking dark energy, though they too must pass the rigorous tests set by cosmic microwave background data, gravitational lensing, and galaxy clustering. The stakes are high. Resolving the Hubble tension could fundamentally rewrite our understanding of the cosmos. What if the expansion rate of the universe changed more abruptly than we currently believe? What if there were interactions between dark energy and dark matter? What if unknown particles played a role in the universe's early development, skewing our interpretations of the CMB? Each of these questions is currently being explored, and the JWST is at the forefront of that exploration. With each new dataset it transmits, scientists gain sharper tools and broader perspectives. It's a thrilling time in astrophysics and cosmology. These mysteries, ranging from the precise value of the Hubble constant to the true nature of dark energy, may soon be clarified through combined analysis of JWST data, ground-based observations, and advanced simulations. Until then, we remain in a state of discovery, learning more with each telescope scan, gravitational wave detection, and spectral analysis. And so, in the silence of the deep cosmos, light travels across time to reach our instruments. From those faint signals, humanity builds models, raises questions, challenges old beliefs, and dares to imagine a deeper, stranger, more magnificent universe than we ever thought possible. As the James Webb Space Telescope, JWST, continues to send back data, the frontier of cosmology grows ever more thrilling. We now stand on the threshold of discoveries that could transform our understanding of time, space, and existence itself. Each new image, each revised measurement, each unexpected pattern acts like a cosmic breadcrumb, guiding us to a deeper understanding of the universe. It is not merely a march forward in science. It is a passage into the unknown, where every assumption can be appended. One of the most compelling revelations brought by Webb's infrared eye is a growing suspicion that our cosmological model may need a fundamental revision. The so-called Hubble tension, the persistent discrepancy between early universe measurements and local universe measurements of the expansion rate, has not gone away. In fact, JWST's observations, which peer across both time and distance, seem to sharpen the tension rather than smooth it out. The realization is both exhilarating and unnerving. The universe may be telling us that something profound is missing from our equations. Consider, for instance, the nature of dark energy. For decades, it has been treated like a mysterious constant, lambda, introduced by Einstein and later revived in light of late 1990s supernova data. Yet what if dark energy isn't constant at all? Some models propose it might ebb and flow like a cosmic tide, undulating, shifting, decaying, over the history of the universe. JWST's ability to observe galaxies at redshifts beyond 10 means we can chart the expansion history across cosmic time. If we detect subtle variations in how fast the universe was growing at different epochs, we will gain clues about the nature of dark energy itself. Is it an intrinsic property of space-time, or is it produced by fields that change value? JWST's images of ancient galaxies may help answer these questions. Then there is the puzzle of galaxy formation and evolution. When astronomers first trained Webb on distant galaxy clusters, they were astonished by what they saw, or didn't see. Some galaxies appeared surprisingly large and evolved earlier than any models predicted they could. It is as if the cosmos is telling us, here are giants that formed in record time. Could our understanding of star formation and gas dynamics be too simplistic? Are there catalysts, perhaps exotic forms of dark matter or feedback from early black holes, that accelerated cosmic assembly? These questions, while technical, touch on the very nature of creation. Gravitational lensing offers another avenue of discovery. When massive galaxy clusters bend light like cosmic funhouses, they distort images of galaxies behind them in ways that reveal the cluster's mass distribution. Webb's precision allows astronomers to detect lensing distortions at unprecedented scales, testing not only dark matter's presence but whether it behaves as expected. Are there clumps or smooth distributions? Does dark matter self-interact? Could there be entire layers of structure that